Okay, guys, so it's, okay, I'm not sure what's going on with this WebEx assistant, but um, it's auto turning on or someone's turning it on, and it's gonna be a huge distraction on the screen if we do that. So I'm turning it off and hopefully this will function right. Anyway, so today is our last lecture, so hopefully everyone's at least somewhat happy about that, right? It's about time for a break. You do still have some things to finish up, so we're going to be talking about nuclear chemistry today. So chapter 15. And so we'll do all we're going to do from the chapter today, meaning that your assignment for this chapter or your assignments and your quiz need to then get done. So your assignments are due tonight, your quiz due tomorrow. So like always, always, when we finish a chapter, you have assignments due by that night and you have a quiz due the next day. This has not changed all semester, with the exception of when I've made an extension because I haven't quite finished, a chapter, but that won't be the case today. And it is a short assignment because we're only spending one day on the chapter. Okay, guys, so if you haven't done it yet, don't worry, it should not take that long. Now you do have final next week. The official schedule is Monday at 8 a.m. for one section and Tuesday at 8 a.m. for the other. But I will do it just like our other tests. I will post it and give you several days to choose which day you want to take it, okay? So it'll be posted Monday morning, 8 a.m. It will be due by midnight Friday. So you have any time during final exam week to take that exam. It will be a timed exam just like all the others, meaning you can't just start it and then come back hours later. Once you start it, you have started the exam and that's that. You need to sit and finish it. So make sure you have good internet connection. Make sure you have the time. I will post some more information once I have it all put together. But basically it's all the content we've covered this semester. So it's chapters 1 to 15 with the exception of, I believe it's chapter 10, whatever the gases chapter is, we didn't do that. Okay. So you can go back and review old study guides. I will post an extra study guide that's kind of condensed for you guys. I'll get to that this afternoon. I just have to, review what I've got on there and remove stuff if we didn't do it. And let's see, we are not meeting Tuesday and Thursday next week. It's finals week, so there's no actual class meetings. You are still welcome to email me or meet with me on WebEx, whatever. Let's see, exam 3, yes, I was working on, I've got some of them finished yesterday. I've still got to finish up grading on others. I'm in the middle of grading for 2 classes, and so I may get them all finished today, but if I don't, you should see your grade sometime tomorrow. I won't open up the exams for review till I get them all completed grading. So some of you that can already see your grade, you're just going to have to wait till either this evening or tomorrow to actually be able to go back and review it. But you will definitely be able to review your your exam 3 results by tomorrow so that you can start studying or reviewing that stuff for the final. Okay. Okay, so I think that's all the just basic general stuff I wanted to mention at the beginning, and I think I've answered the questions. Okay, so let's get going with nuclear chemistry. So let's see if my mouse will work. Maybe. Here we go. Okay, so with nuclear chemistry, okay, sorry guys, here, I can move this. Okay, so I don't know if you're seeing captions on your screen and you don't want to, I guess you might be able to close those. I don't know why it has to pop up everywhere, but whatever, it'll work. Anyway, with nuclear chemistry, you need to be familiar with what radiation is, Okay, so we talked about radiation a little bit back in chapter 7. We talked about electromagnetic radiation, okay? But there are other types of radiation. But basically, it's any kind of transmitted energy, okay, that is going to travel through matter or space. So it depends on the type of radiation, on if it can travel through both or how far through matter it can actually travel. And so our two kind of types of radiation are electromagnetic, so light, that's what we talked about back in chapter 7, so visible light, infrared, ultraviolet, and so on. Those are types of radiation, and so that is just energy that passes through space. It can pass through different matter, depending on what type of matter and what type of light. But what we're going to focus on more so in this chapter is particulate radiation, okay? And so particulate radiation actually has mass, you know, it's part of it, whereas electromagnetic radiation is purely energy, okay? So you can have either type. And so really with nuclear chemistry, most often our focus is on the particulate type. And so it's typically some mass, some portion of an unstable atom that gets released for one reason or another. Okay, so it can be beta particles, alpha particles, positrons, protons, neutrons, you know, all kinds of stuff. And so we'll be looking at that a little bit. Now, your book does give you a table to tell you about some different types of radiation. Their notations. We'll look at that a little bit closer in a few slides with a more complete list. But in this, it kind of gives you a little bit of an idea of the things that we would be interested in with respect to the different types of radiation. So not only how you notate it, so how you would write it, a shorthand form, like to write in an actual reaction, but also the mass of the particles, the charge of the particles, which you're going to see in the different types of notations. Okay, so we'll look at that a little more in depth. But also in this table, it talks about the penetration ability of these things. And specifically, they give you an example of how well it could penetrate into a sample of aluminum. Okay, so aluminum's a metal, it's a relatively soft metal. And so some particles can, you know, penetrate pretty deeply in there, some only go a very short distance. And it all has to do with the penetrating ability of those particles. But another important concept that we also talk about other than penetrating ability is ionizing ability of something, okay? So ionizing ability or ionizing power helps us understand kind of how much damage the particles can do. So different particulate radiation will have different capabilities to ionize things, okay? Even, you know, types of light or electromagnetic radiation could ionize things. And so any type of radiation potentially has the capability to ionize something. When I say ionize, that means that it's knocking electrons off of something. So it knocks electrons off and creates then a cation, okay? And how well something can do that depends on its mass, okay? And the more massive the particle or the larger it is, the greater its capability of ionizing something, okay? So if you throw some really large object at something, it's going to do a lot of damage. Whereas if you throw a very small object at something, it's going to do a lot less damage. Okay, so you can think of it that way. Ionizing power is giving us an idea of how much damage these particles can do. So something with a large ionizing power or a great ionizing power can do a lot of damage, meaning it can actually be kind of dangerous, okay? Because most of the time when we're focused on this, we're thinking about our exposure to it, okay? So if we're doing nuclear chemistry and these particles are coming off, then we need to be aware how much damage they can do to us, okay? But then the other part, like I was saying, has to do with their capability of penetrating into something, okay? And so that's the part where in the table they talk about the example with aluminum. So we can talk about particles in terms of their penetrating power. So how well they can penetrate matter, meaning go through matter or go into matter, okay? And that also in some ways depends on the mass, okay, or the size of the particle. If you have a very large particle, it's going to get stopped by the surface of something, okay? It's not going to go through. It eventually is going to get stopped. It can do damage to the surface, but if it has a large mass, it's not necessarily going to just break through very easily, okay, because it gets stopped by all the matter. But if you have a very small particle, it can kind of squeeze between things essentially. So if it hits this surface hard enough, and it kind of can find the holes essentially and go through. So it tends to penetrate deeper if it has a lower mass or is a smaller particle, okay? Also, what plays a role in how well something can penetrate something else is the charge, okay? The lower the charge or smaller the charge, the higher the penetrating power. And that's because when you have charged particles, they tend to attract to different things. And so if something has a charge, it's more likely that it gets attracted to something at the surface or something a little ways into a material. And it slows it down and kind of stops it. Whereas if you have a neutral particle, it isn't going to be hindered at all based on interactions because it's not really going to want to interact with anything. Okay, so something with a low or no charge has a higher penetrating power than something that is charged. Okay, so those are really important terms that come up when we're talking about different types of radiation, just to understand a little bit about their impact, how they would actually affect you if you're exposed to them. Okay, now let's talk about radioactivity. So radioactivity is kind of what you're looking at with a lot of nuclear reactions, okay? It's really a type of spontaneous nuclear reaction, meaning it is a type of nuclear reaction that happens naturally. It happens kind of on its own, okay? And it's a spontaneous loss of energy due to the emission of some particle from a high energy particle, okay, or a high energy unstable nuclei, okay? Now, it could be the emission of particulate radiation. It could be the emission of electromagnetic radiation. Sometimes both are emitted, sometimes only one or the other, okay? But when you have some radioactivity or some spontaneous nuclear reaction occurring, there is always going to be some loss of energy. Now, when I say loss of energy, I mean emission of energy, okay? So we don't actually lose or create energy, okay? But by those particles coming off of there, energy is actually coming off as well, okay? And with this, we talk about an unstable nuclei, or unstable nucleus. Nuclei is plural, but I have in parentheses there nuclide. So it's important for you guys to realize that when you're talking about nuclear chemistry, when people are talking about nuclear reactions, instead of using the term nucleus or nuclei, they'll talk about nuclides, okay? So a nuclide is just an atom of a specific isotope of an element, okay? And it's really focused on the nucleus, even though there are electrons around it. The focus is the nucleus and what particular nucleus of this element we have, okay? So that term nuclide really is talking about a particular isotope of an element. So say we have carbon. Well, carbon, we can have a carbon 12 atom, we can have a carbon 13 atom, a carbon 14 atom. And so all of those isotopes of carbon have differing numbers of neutrons, okay? So they all have the same number of protons because they're all carbon, okay, which you get from the periodic table. You look at the periodic table and you'll see an atomic number of 6 with carbon, meaning no matter what isotope of carbon we have 6 protons, okay? So we learned this way back in chapter 2. So in some ways, this is a good little review. But then just remember that for a given element, you can have different neutrons in the nucleus, okay? But with nuclear chemistry, it's important we know which one you're talking about, because different isotopes of an element will react completely different in terms of a nuclear reaction, okay? Now, in addition to just using the general term nuclide to say that we're talking about a specific isotope, we can also use the terms parent nuclide and daughter nuclide when we're referencing a nuclear reaction, okay? So the parent is the reactant and the daughter is the product, okay? Now, when this happens, like I've got above, you can have, particulate radiation coming off or electromagnetic radiation coming off. So you have additional products, okay? Or sometimes you'll be bombarding something, so you might have an additional reactant, which are just other particles. So those aren't really the parent and daughter. The parent and daughter are the actual element that is reacting, the specific isotope of the element that's reacting. So we'll see that when we start writing reactions. I'll point those terms out to you again. Now, when we have different nuclides, some of them are stable and some of them are not, okay? So when we talk about radioactivity, we're talking about spontaneous reactions that occur. And so that would involve radioactive nuclides. So ones that actually aren't stable naturally as they are, okay? So those are ones that will on their own just start to break down, okay? So they'll release matter or energy or both by way of this radioactive process. So some decay, okay? And so they will give off some sort of light or give off some sort of, ionizing radiation. So some sort of particle, an alpha particle, a beta particle, so on, okay? So we're going to look at the different types of radioactivity that can occur, okay? Now, another term that comes up sometimes when we are talking about nuclear reactions is nucleon. This is just a combined term to reference all of the particles in the nucleus, okay? So when we talked about atomic structure back in chapter 2, we talked about that an atom has a nucleus, and in that nucleus are protons and neutrons, okay? And that there's electrons around that. Well, in your nucleus, those protons and neutrons can be discussed independently. So you can talk about the positively charged particles, and those are the protons, and you can talk about the neutral ones, those are the neutrons, or you can talk about them as a whole, okay? And as a whole, they're nucleons, okay? So each one of them is a nucleon, whether it's a proton or a neutron, okay? So that's an important term that you should be familiar with as well. Now, before we go into reactions, you're going to need to know how we actually write this stuff, because it's a little bit different than a typical chemical reaction. So we're going to bring back a notation that you've seen before, but we use it a little bit different, okay? So when we're talking about nuclides or any kind of nuclear particle, and so it could be, your alpha particles, beta particles, whatever, we're going to use a notation that we called before isotope notation or atomic notation back in chapter 2. So this AZX symbolism to help us communicate what nuclides we're dealing with and what particles we're dealing with. So remember, at the top, that's called the mass number. Now, in terms of nuclear chemistry, you could simply say it's the mass of that thing, okay? Whether it's an isotope of an element or it's a particle, it's the mass of that thing, okay? Or at least rounded to a whole number. And then the bottom number, we normally think of as the atomic number, right? When we did this for just regular atoms. But in nuclear chemistry, that spot is also used to indicate the charge, okay? So we don't put a charge at the upper right. The charge is actually at the bottom left. If it doesn't have a sign next to it, it's because it's a positive charge, and that would be indicating the positive charge, meaning the number of protons, okay? So in a sense, it's still the number of protons, but when we want to designate things like electrons, you'll have like a -1 down there. Or if you want to designate something as being neutral, then it's going to have a 0 down at the bottom, okay? So you're best off thinking of this AZX notation as mass, charge, and then symbol. And so that symbol can be the element symbol, okay? It can also be just the symbol we use for whatever nuclear particle is being given off, okay? So we've got a table here that gives you all the different variations of particles that we will deal with our nuclear reactions, okay? And there's several of them. I give you multiple options. I think what I have on the left for each of those is the more proper notation. So that's usually the way it's written for most nuclear chemists, okay, how they would write it. But the symbols I have next to them that I say or, you know, those are also acceptable alternatives. Generally, you know, people accept those. So we can have an alpha particle. So an alpha particle we would symbolize usually as an alpha, okay? And an alpha particle has a mass of 4, so the top number is 4, and it has a charge of 2, meaning it's got a positive 2 charge, and so that's on the bottom. And that's because it's got 2 protons, okay? And so if it has a mass of 4 and it has 2 protons, then it's actually got 2 neutrons, okay? Because the total mass of something is the sum of its protons and neutrons, okay? Always. And since that has 2 protons in that particle, it is the same thing as a helium nucleus. So if you look at the periodic table and you look for atomic number 2, that's helium. And so sometimes instead of writing it as an alpha, people write it as He, because it's a helium nucleus, an alpha particle. And then we have beta particles. Now, this can be a little confusing sometimes because technically there's 2 types of beta particles. There's a -1 and a +1. If we just use the term beta particle, we're talking about the -1, okay? So the first one listed, which is an electron, okay? It's just, I guess, a fancy name for an electron, a beta particle, okay? And so that typically is symbolized with a beta symbol, okay? So it looks like a fancy B. And then it's got a 0 mass, so the top number is 0, and it has a -1 charge, so there's a -1 on bottom. But since it is simply just an electron, we could, for the symbol, write it as an E, okay? But you still have the 0 and -1. But we can also have a positively charged beta particle, which we would typically call that a positron, okay? So try not to let this table confuse you too much. This is the primary name here, beta particle for this, and then positron is what we would call the positively charged one. I won't ever refer to the positive one as a beta particle, but I just want to make sure you know that technically it is considered a beta particle. Okay, it just has a positive charge. So it still has a mass of 0, okay, a 0 on the top and a +1 on the bottom. And we would usually symbolize it as a beta, but you can also symbolize it as an E, okay, just like you can for the electrons. And then we have gamma rays. Gamma rays we talked about back in chapter 7 with light. Because it is a type of electromagnetic radiation. It's actually the highest energy electromagnetic radiation. So it actually ends up coming up quite a bit in nuclear chemistry. But since it is just light, it has no mass and it has no charge. So the numbers that go with it are 0 and 0, and we use a gamma to symbolize it, okay? And then we have protons, and so protons have a mass of 1, they have a charge of 1, so we have 1, 1, and then you can symbolize it as a P, or you can also symbolize it as an H, because when you have one proton, you have a hydrogen nucleus, because you look at the periodic table and a number 1 for protons is always hydrogen, okay? And then lastly, we have neutrons. And so that has a mass of 1, no charge, so a 0 on the bottom, and we symbolize it with an N, okay? So again, you need to be familiar with these symbols, okay? The names and the symbols, okay? Or be able to utilize this table and pull those from it so that you can write reactions. And keep in mind, some of those can be written in 2 different ways. And like I said, the first way I have each written is usually the way people write it. And that's normally the way that it's expected to be written. Although, like on a test, I would accept either. Okay. Okay. So let's look at some examples of some radioactivity. Okay. So there's some common types of radioactivity. And the first is alpha decay. Okay, and alpha decay it should be what it sounds like, right? It involves an alpha particle and it's a decay. And so actually a decay is always something breaking down. And so it's breaking down and giving off an alpha particle. Okay, so alpha decay or alpha emission, if you want to call it that, is the spontaneous emission of an alpha particle. And so remember, that is actually a helium-4 nucleus. And so you have some unstable nuclide that's giving this off, okay? And so this always is going to have kind of a general form for the nuclear reaction. You have some parent nuclide that you're starting with, okay? So this, what I have symboled as AZX, that's my parent, okay? That's my parent nuclide, and it gives off an alpha particle, right? This is my alpha particle. And what results is now I have some daughter, okay? I have a daughter nuclide that forms from that, and that daughter has to have a mass that is 4 less than what your parent started with. So if your parent's mass is A, then your daughter's mass must be 4 less than that, okay? Because a mass of 4 went to the alpha particle, okay? Whereas if your parent starts with a charge of Z, then your daughter, in this case, must have a charge 2 less than that because it gave up a positive 2 charge, okay, to that alpha particle. So in a nuclear reaction, we write things using this symbolism, this AZX type symbolism, showing the mass, the charge, and the symbol that represents that thing. But we need to balance those reactions. And by balancing them, we typically aren't writing a number in front of things. It's just the total mass on each side needs to equal, and the total charge on each side needs to equal. So if you have an alpha decay, the reaction's always going to follow this pattern, okay? But of course, there's going to be actual numbers in there instead of A and Z, and there's going to be actual symbols instead of X and Y. So let's look at an actual example, okay? So you can have uranium-238, okay? So that has a mass of 238. U is the symbol for uranium, and 92 comes from the periodic table, okay? And if that undergoes alpha decay, then it's going to form thorium-234. And even if I didn't tell you that, you should be able to figure it out. So if I told you you had uranium-238 and it decays by alpha decay, then I would be telling you that first thing and kind of that last thing. And you should be able to figure out this thorium part, okay, just by doing some subtraction. And so you'd look and say, okay, 238 over here, okay, And then on the right side, you would have 4 plus something, and that needs to equal 238. Okay, and so that x is 234. Okay, whereas then the bottom number, the 92, must be equal to some value, okay, plus 2, because that's the bottom number on my alpha particle. So that x that makes this true is the 90. Okay, so you should be able to figure out the numbers of any missing particle in a nuclear reaction by just kind of subtracting and adding things, you know, making sure each side is equal. Okay, and then once you have those numbers, that bottom number of 90, you could look at the periodic table and find the element symbol that goes with that. Okay, so that reaction, sometimes you would be given that completely, and just by looking at that reaction, you should be able to tell me, well, there's an alpha particle produced, so that's an alpha decay. Okay, you should be able to recognize that. But if I hadn't have given you the reaction and I just told you a little bit of information, you should be able to write the reaction as well. Okay, or fill in blanks. Okay, so let's look at another example of an alpha decay. Okay, but this time I'm not telling you everything. I want you to tell me what the daughter nuclide is in the decay of thorium-234, okay? Or sorry, in the alpha decay of thorium-234, okay? So in this, thorium-234, if you're ever given an element and then a dash and a number, okay, that's telling you the mass number always, okay? We talked about this back in chapter 2. So that's the top number. Okay, which I've rewritten as the symbol there, okay? And I didn't give you the bottom number. And in order to figure this problem out, you're gonna need that bottom number. So you would look at the periodic table. Now, I do have thorium in the example before, so we know that bottom number is 90, okay? But you could look at the periodic table, find that symbol, and the atomic number is what then goes on the bottom. So we have those, but now I have this blank, okay? And that's where the daughter goes. And I want to know what that is, okay? So here I would say, okay, well, I have 234 on the top for the left, and that needs to be equal to some value plus 4, okay? And so that must mean that my top number has to be, here my x has to be 230, okay? And then down here at the bottom, I have 90 must be equal to some value plus 2, okay? Because some of my bottom numbers need to equal on each side. And so in this case, my x would have to be 88, right? And so now, since this stuff's kind of going to be in my way, I'm going to erase it and write what that gives me. Okay, so I figured out my top number needs to be 230. Okay, so I'll write 230 on the top, and my bottom number needs to be 88. And then I need the symbol for that. So I'm going to have to look at the periodic table because I don't have that memorized. I don't know what 88 is. And so I look at the periodic table and let's see, 88. Where is 88? Oh, it's RA. Okay, so it's radon. Okay. RA or radium. It's one of those. Okay, so we have that. And that would be then our balanced reaction. But in this, it says, what is the daughter nuclide? Okay, so the daughter nuclide is either you could say 230, 88, and then, oops, sorry, RA, okay? Or you could say that it's RA-230. Both of those would be, I guess, acceptable answers. It just depends on which way, you know, you're asked to communicate it, okay? And so that is our daughter, okay? Okay, guys. Now, both of those examples, they follow that general form as that initial one that I wrote, right? Because we always have an alpha particle as a product, and our daughter always has a mass 4 less and a charge 2 less than the parent. Okay, so that's our alpha decay. That one's a really common type of radioactivity. Okay, so you got to be familiar with that. You should be able to write reactions for alpha decay of different particles. Now, let's look at another really common type of radioactive decay. So we can have beta decay, and so it's also kind of what it sounds like. It's the emission of a beta particle, or here I say a spontaneous ejection of a beta particle. Ejecting, emitting, release, all of that stuff is the same thing, okay? So a beta particle is coming off of it, okay? Or you can say an electron, right? A beta particle is an electron by some unstable nuclide. And actually, it's a neutron-rich nuclide, okay? And so what I have here first is the general form of any kind of beta decay, okay? So for any beta decay, there's a beta particle as a product, okay? So you have your parent, so our general parent, AZX, okay? And it emits a beta particle. And so the resulting daughter for that is going to have the same mass because the beta particle has no mass, okay? And its charge is actually going to be one higher than the parent because it's releasing a negative. So the daughter actually is more positive than the parent, okay? Now, that second reaction that I have written is just to try to help you understand what's going on. Because let's stop and think about this. We're talking about a nucleus, and this nucleus is ejecting an electron. And you should stop and think, how is that even possible? Because there's no electrons in the nucleus, right? The electrons are outside of it. But what's really happening is within that nucleus, you have neutrons and protons. And this nucleus is unstable as it is, but what it can do is it can split one of its neutrons, and when a neutron is split, it gets split into a proton and an electron, okay? And the proton can stay in the nucleus, okay? Because that's where it should be, right? But the electron cannot remain in the nucleus, okay? It's not possible. So what happens is a neutron will split and the electron gets kicked out, okay? And so it gets emitted. And so a beta particle is coming off. And so that happens when the nucleus has too many neutrons. So how it fixes it is it breaks apart a neutron and kicks out the negative charge that comes off, okay, that beta particle. And so that helps to reduce the number of neutrons in the nucleus. Okay, so one example of this is if you have a carbon-14 nuclide, it can emit a beta particle. And when it does that, it forms nitrogen 14, okay? And so if we look at this, this should make sense. We have 14 on the top of the left, and on the right, we have 14 plus 0. And those things are equal, right? It's a mass of 14 on both sides. And then on the bottom, I have a 6 on the left, and then I have a 7 and a -1 on the right. And so these need to be equal when I sum them, right? So if I take 7 plus a -1, it gives me 6. And so that makes sense, okay? So my daughter particle here has a charge 1 greater than the parent, okay? And since that bottom number changed, I actually have a different element, okay? So nuclear reactions are different than a chemical reaction. So throughout the rest of the semester, we were talking about chemical reactions where bonds are being broken and new bonds are being formed. And that all involves electrons, okay? Sharing of electrons, sometimes even transfer of electrons, whereas all these reactions we're talking about now involve changes in the protons and neutrons, so things in the nucleus. So since we're changing the nucleus, we could be changing what element we have, okay? So you don't need to be concerned with the fact that there's carbon on the left and no carbon on the right, okay? That is possible in nuclear chemistry, okay? What needs to be true is the mass and charge remains constant. Okay, now let's look at another one. Here I say, what's the daughter nuclide produced by the beta decay of strontium-89? Okay, and so then I have strontium-89. Here I didn't give you the bottom number, and we don't have it anywhere above, so we're going to have to look at the periodic table and find strontium, and its atomic number is 38. So I'm going to put a 38 on the bottom, okay, so that I can kind of balance this reaction. And then I look at my top numbers. I have 89 on the left, and right now I have 0 on the right. So my top number is definitely going to have to be 89, okay, so that they both equal 89. And then the bottom number, I have 38, and on the right, I have -1, okay? So I have to think about what plus -1 gives me 38, and that would have to be 39. So 39 plus a -1 gives me 38. And so that would balance my charge. And then 39, I look at the periodic table, find what element that corresponds to. So 39, that's yttrium. So that's a Y, okay? And so that reaction is balanced. So if you were asked for the reaction, you'd write all of that out. But here it says, what's the daughter nuclide? And so your answer is 89, 39, Y, okay? Or you could say, you know, Y dash 89, or you could write out the element name dash 89, okay? Any of those would be okay. So be careful when you are doing the homework, pay attention to what it's actually asking for. If it asks for the daughter nuclide, only provide that one symbol, although you have to write the whole reaction to figure it out, okay? But provide the answer that it's asking for. Okay, so just be careful with that. Okay, now let's look at some more. So those are our two most common types of spontaneous nuclear reactions, so our radioactive decay. But there are a few others that come up that it's good to be familiar with. So another kind of common one is positron emission, okay? So again, you have some unstable nucleus, and it's just like what it sounds. Positron emission is the emission of a positron. So you need to know that a positron, remember, is a positive beta particle, okay? So that has to be a product, which you see here as a product, right? And so if we have our standard kind of parent, our AZX, and it emits this positive no mass particle, then what happens is that daughter has to have the same mass, but its charge is going to be 1 less, okay, because it lost a positive charge. Okay, so that's your general form for any positron emission. Now, again, you should kind of question this. You should say, okay, I have a nucleus and somehow it emits a positron, but we've never talked about a nucleus having a positron before. We talk about it having a proton and a neutron. So again, this involves your protons and neutrons, and it involves the proton splitting, okay? So whereas the beta emission has to do with a neutron splitting and releasing an electron, okay? A positron emission is really happening with a nucleus that has too many protons, and how it fixes that is it breaks apart a proton. And the result is essentially it's taking the charge from that particle, okay? So it's splitting the charge off and leaving this neutral, particle. And so that neutral particle that's left behind is the neutron, and the charge is the positron that gets then kicked out of the nucleus, okay? So it comes off as a positron. That's really what's happening. Now, another type of radioactive decay we could have is gamma ray emission, okay? And remember, gamma rays are just a type of electromagnetic radiation. And so it is just purely energy, okay? So you have some unstable nucleus that just has too much energy, and one way it can get rid of that excess energy is by emitting a gamma particle, okay? Now, when it does this, if it really only releases a gamma particle, you have no change other than the energy. And so notice on this one, we have the parent is AZX and the daughter is AZX. Because if you emit just energy, the mass doesn't change and the charge doesn't change, okay? So that, when that happens, we usually wouldn't just, write that reaction because it looks like nothing's happening. But where this is important is usually this happens right alongside with other things. So sometimes you'll have an alpha decay, and along with the alpha particle that's coming off, you also get gamma rays. Okay, so you also have these high energy particles coming off. So they happen in partner with other things, the gamma ray emission. So we won't really write reactions that have gamma rays, but I figured I'd throw it out there because occasionally you run across it. Now, the last one that we'll look at that is relatively common is electron capture reactions. And so this is another type of spontaneous radioactive decay, but it's a little unusual, okay? So again, the name kind of hints to you what's going on. It says electron capture. So you have a nucleus and it is capturing an electron. It is taking in an electron into the nucleus, okay? And so where that electron comes from is from that atom, okay? So if you have some isotope of an element and it's unstable, occasionally to fix its stability, it can essentially steal one of its own electrons. So it'll pull one of its own electrons into the nucleus. And when it does that, you have to remember, again, electrons don't exist in the nucleus. So when it pulls that in, it needs to transform it. And so what it does is that electron combines with a proton and it forms a neutron. Okay, so it becomes something that can exist in the nucleus. Okay, so in an electron capture reaction, you always have an electron as a reactant. Okay, and so this is the one type of radioactive decay that looks a little bit different. Okay, so you have a reactant for this one instead. So you still have your parent, but the electron is reacting with it. And so in that case, the daughter, it still has the same mass because it's taking in something that is massless or has a negligible mass. And then the charge goes down because it's taking on something with a negative charge. And again, what's really happening is that electron, once it's pulled into the nucleus, it combines with a proton, meaning the charges then cancel. And then it just has that mass of 1, so it's a neutron, okay? Okay, now, those are just general types of radioactivity. So when you have some radioactive nuclide, so some nuclide that is not stable, those are things that naturally will happen to them to make them more stable, okay? Now, nuclear reactions can get more complicated, okay? And we can force nuclear reactions, okay? So we can cause them to happen if we want to try to manipulate some nucleus. And so we can do it by way of what we call nuclear transmutation, okay? Or more simply, nuclear bombardment reactions, okay? So these are non-spontaneous nuclear reactions. And so in these non-spontaneous nuclear reactions, the nuclei, we bombard them with a beam of usually neutrons. So essentially we're throwing something really hard at this nucleus to try to get it to react, to get it to essentially break apart, okay? And so usually it's shooting a beam of neutrons at this particular nuclide. And if you do this with enough energy, if you throw them at it fast enough, you can cause the nucleus to break apart. And a lot of times it not only splits into, say, 2 different nuclides, a lot of times other particles are going to come off. And sometimes those are even more neutrons. So you put in neutrons, and those are really just to kind of bombard it, give it enough energy. but then small particles can come off in the process. Now, this is a process that's used to actually create some of the radioactive isotopes. So things that have a Z value greater than 92 are actually unstable. So everything on the periodic table with an atomic number greater than 92 is actually unstable. They naturally radioactively decay. And so they're going to be created somehow, okay? So we can create them in the lab by doing this type of stuff, by doing nuclear bombardment reactions. So we can create then these unstable nuclides, which then we can utilize for different things. Now, when this is done, this isn't something you do in a typical chemistry lab, okay? This requires specialized equipment, of course, and also, you know, protection, because nuclear reactions can be dangerous if you don't do them in the right environment, okay? So you can find information in your book about this. You don't really need to know this part, but I figured I'd throw it in there anyway. And so sometimes when people talk about nuclear reactions, you'll hear them talk about a linear accelerator or a circular accelerator or a synchrotron. Those are just big facilities that they use to induce nuclear reactions. And so these are huge setups that can then shoot beams of electrons or neutrons, you know, at different nuclides to then induce these reactions, okay? And whether it's linear or circular, that's just really the setup. It's either a very long hallway, essentially, or it's this circular one that the particles go around and around and around until they collide then with that nuclide, okay? And so it can be, you know, a complex process, actually trying to induce some non-spontaneous nuclear reaction, but it can be done. Now, let's do a few more practice writing reactions, because this is kind of the most important part for you guys. And so we can write some nuclear equations. Here I say write the nuclear equation for the alpha decay of 241 americium. And so that's 241 AM. And so that is my parent, okay? And I want to write the alpha decay of that, okay? So I know this particle, that's my parent, and I know that I need to be producing an alpha particle, so a 4,2 alpha. And then there must be something else. There's got to be a daughter produced in order to balance this reaction. So I need to figure that out. So I can look at the top numbers, and I have 241 on the left, and I have 4 on the right, and then I need something, okay? And in this case, that's going to come out what? I have 241 minus 4, that gives me 237. So I should have some particle that has a mass of 237 as a product, okay? And then the bottom, I need to balance the charge, okay? And I didn't give you the bottom number on this. So I'm going to have to look at a periodic table. So let's pull up a periodic table and let's find this americium. So we have that down here, okay? So there, and this 95, that is my number of protons or my charge for that. So 95 is my bottom number in this case, okay? So I put 95 here, and so that'll help me get the rest of this. So 95 should be equal to 2 plus some value, okay? And so 95 minus 2 is going to tell me that that bottom number is going to have to be 93, okay? So my bottom number here is going to be 93, and then I need to know what element symbol to put with that. So let's go back to the periodic table, and let's find 93. Here we go. Here's 93, and that's like Neptunium or something. So NP, okay? So NP is my symbol. So this would be the nuclear equation, okay? That's my nuclear equation, or my nuclear reaction for the alpha decay of AM241, okay? Okay, let's do some more. Okay, so next one, I say determine the identity of the daughter nuclide from the beta decay of lead-214. Okay, now all I want to know is what's the daughter nuclide. You could try to reason it out without writing the reaction, but I would just write the reaction to figure it out. Okay, so we have a beta decay of lead-214. So you need to know lead is Pb. Okay, you guys should know that. We work with lead enough. And lead-214 means the mass is 214. And this needs to undergo beta decay. So it's going to produce a beta particle, so 0, -1, beta. And then there's got to be something else, okay, that daughter, and that's what we're looking for. So the top numbers, I've got 214 on one side and 0 on the other right now. So 214 must be my top number. And then my bottom, I need to know what's lead. Okay, so if I go back and find lead, here's lead. So lead is 82. Okay, so I go back and lead is 82. Sorry, that dark. 82. And so I have 82 on the bottom for the left. And so the right needs to total to 82. Right now I have -1. And if I add 83 to that, it gives me 82. So I go back again, and 83 here is to the right. And so that is bismuth. And so I have Bi. Okay, so in this case, it says determine the identity of the daughter nuclide. So my answer here is just that. Okay, that's my answer. But you've got to write the reaction to figure it out. Okay, next one, I say determine the identity of the daughter nuclide from the electron capture by rubidium-81. Okay, so I have rubidium-81, so Rb, and it's 81, okay, is the mass, and it's an electron capture. So it is reacting with an electron. An electron has a mass of 0, charge of -1, and it's an E, okay? And so then that is going to produce some other nuclide. And so my top numbers add to 81. So the product's going to still have a mass of 81. But then the bottom numbers, again, I need to figure out what that is. So I go back and I find rubidium's here. And it has an atomic number of 37. So that's my bottom number, 37. And then my bottom numbers, if I take 37 plus a -1, that gives me 36, okay? And again, go back to the periodic table, look for 36. In this case, that is krypton, okay? And so I have Kr. So this is my daughter nuclide for that process, okay? Okay. Now, next up, here I say determine the identity of the daughter nuclide from the alpha decay of radon-224. Okay, so we have Ra224, and that is undergoing alpha decay. So I have 4, 2, alpha, okay? And so then there has to be some other product, my daughter, that I'm trying to figure out. So again, look at the top. I have a total of 224 on the left, 4 on the right, so I need 220 on the right, okay, to make 224. And then I need my bottom number for Ra, and so in this case, I go, and there it is, it's 88 on the bottom. So I have 88. And then my bottom needs to total to 88 then. I have 2 right now on the right, so I need to add 86 to that. And then again, we go back and look for 86, which in this case is Rn, which actually I think Ra is radium and Rn is radon. Sorry, I think I said that wrong a few times. So we have Rn is radon. This is radium. Okay. And so that would be my daughter nuclide, okay? Then next up, we have determine the identity of the daughter nuclide from the positron emission of oxygen 15. So I have oxygen 15, and it's going to undergo positron emission. So a positron has no mass, positive charge, and that is a positive beta particle. Okay. So then I need to figure out my daughter, right? The mass is 15 on the left. The mass needs to total to 15 on the right. So 15 plus 0 gives me 15. And then oxygen, you look at the periodic table, and here's oxygen, and my charge is 8. Okay, so there's actually an 8 on the bottom here. And so the charge on the left is 8. On the right now I have 1. And so I need to have 7 added to that to make 8. So you go back and we have nitrogen, okay? So N would be my symbol with that. And so that is my daughter nuclide, okay? So pay attention to the question. Here I'm asking for the daughter nuclide. I could also just ask you for the reaction as a whole, and it's the whole thing. You've got to know those particles, or, have that table out and be able to look up those particles and be able to recognize, is this particle supposed to be a product because it's a decay or an emission, or is it a reactant because it's an electron capture? Okay. Now, let's talk a little bit about the stability of nuclides. And so why something would undergo, an alpha decay or a beta decay or a positron emission, okay? So it's not all random, and there is some amount of predictability to it, okay? It all has to do with the ratio of neutrons to protons within a particular nuclide, okay? So within a nucleus, remember, you have these protons and neutrons, and they're all really compact. They're really close together, okay? And it works out kind of okay when you have these neutral particles and the positive particles, okay? But if you have too many of the positives, then those positive charges are really repelling each other, okay? And so then that starts making it unstable. So there's a certain ratio that there needs to be. And as the nucleus gets larger, you kind of have to pack in more neutrons to shield those positive charges from each other, okay? So sometimes people will look at it in terms of simply, what's my positive charge in the nucleus? So what's my Z value? If you have a Z value less than 20, then generally the nuclei are stable with about a 1-to-1 ratio of neutrons to protons. Whereas when you get a lot more protons in the nucleus, when you get up to say 40, then you need to have a larger ratio of neutrons. So about 1.25 to 1, okay? Whereas when you get even larger, closer to around 80, then the ratio becomes more like 1.5 to 1, okay? But this is just a general, these are general ranges, which aren't the most useful, okay? So you can actually use a plot that tells you about stability to figure this out as well. And so this is the way that typically someone who's working with nuclear chemistry gets a sense for, is this a stable nuclide or not? Okay, now if they work with something a lot, they may know off the top of their head, but otherwise they compare it to this plot of stability, okay? And so on this plot, on the y-axis we have N, on the x-axis we have Z, and so you could figure out, okay, this nuclide has so many protons, and so you could go on the z-axis, find that number of protons, and you can draw a line up to that dotted line. So all the dots, those are the stable cases, okay? Whereas that straight line, it's just showing you N over Z of 1. So it shows you that that stability curve kind of breaks away from it as the Z gets too high, okay? So one way to predict whether a nucleus is stable or not is to use this actual chart, okay, this actual plot. So if you're a nuclear chemist, or someone who works with nuclear reactions a lot, you would have this chart on hand and actually look up things. But you can also use the periodic table and estimate it based on the average atomic mass. So when you look at the periodic table, remember, in addition to the atomic number, there's the average atomic mass. And that actually gives you a sense of the approximate mass that is stable. So you could calculate the N from that value and get an idea of, is this in the stable range? Okay. We're not going to look at that any further. It's just good for you to realize that there are several ways that you can go and look up and figure out, is this a stable nuclide? But by understanding kind of those different types of decay, you should be able to predict or understand what would happen if the N over Z is too high or if the N over Z is too low, okay? Because this is kind of what we were already talking about with respect to some of the decay, okay? So if you have an unstable nuclide, and if you're told that the N over Z for that unstable nuclide is too high, what that tells you is there's too many neutrons, okay? If that ratio is too high, there's a lot of the stuff on top, right? Or there's too much of it. So there's too many neutrons. So your nucleus needs to find a way to get rid of neutrons. And it can't simply kick out the neutrons, okay? But what it can do is break down the neutrons. And if it breaks down a neutron, it creates a proton and an electron, or a beta particle, right? And that beta particle gets kicked out, okay? So it actually ends up undergoing beta decay. So any nuclide that has an N over Z that's too high will naturally undergo beta decay to become more stable, okay? Whereas if the N over Z is too low, that bottom number is too high, meaning there's too many protons. And when there's too many protons, your nucleus needs to figure out how it can get rid of protons, okay? And it could do that most easily by splitting the proton, just like it can split a neutron. So if it splits a proton, it splits the charge off of it, okay? So a neutron gets created and a positive beta particle, or a positron, gets created, and that gets kicked out, okay? And so the most common way an N over Z that is too low will fix itself is by undergoing positron emission. Although there are those other options I have listed there. They can undergo electron capture or alpha decay. It can be kind of complex, but there are some basic things that you should understand. What does it mean if our N over Z is too high? I have too many neutrons. And to get rid of neutrons, beta decay works, okay? And if N over Z is too low, that means you have too many protons, and to get rid of protons, a nucleus is going to do a positron emission, most commonly, okay? Okay, so that's kind of the basics of nuclear reactions and, why some nuclear reactions happen. But then let's at least talk a little bit about some applications, okay? So first, I want to point out some information about energy. Okay, so nuclear energy. There's kind of two basic types of nuclear reactions that are used to get nuclear energy, or attempted to be used to get nuclear energy. The first one is nuclear fission, okay? And this is the actual type of nuclear reaction that occurs in a nuclear power plant. So they perform nuclear fission reactions. And what that is taking a heavy nucleus and splitting it into two or more lighter nuclei. And usually then also some neutrons are coming off, okay? And so essentially you have one reactant and it's breaking up into multiple. That would be a fission. So actually some of those natural radioactivity, so alpha decay, beta decay, those are a type of fission. It's just a super simple type of fission, okay? So when we're talking about a nuclear power plant, it actually is a much more complex fission. But in order to get these more complex fission reactions to occur, the non-spontaneous ones, you have to kickstart it, okay? And so usually it's done by some sort of bombardment, okay? And so we bombard things with neutrons or something to get this process going. And the nice thing about nuclear fission is it releases a lot of energy, okay? The downside is it creates a lot of waste, okay? And so that can be okay if it's managed right. It needs to be contained and taken care of properly. And that's done in a nuclear power plant, okay? Now, with this, so needing to be started can, be a little bit of an annoyance. You have to kickstart it. But the other nice thing about that is that once you get a nuclear fission started, it's going to, on its own, start to release neutrons. So when it splits up, also some neutrons come off. And what happens is it can create then a chain reaction. So that if some of the reactants react, then it releases some neutrons, and those neutrons go on to cause more reactions, okay? And so that's really nice. Even though we have to put in some initial energy to get it started, it produces so much it's worthwhile because it can cause itself to keep going, okay? And with this, it basically just, you need to start with enough stuff. And how much is called the critical mass, okay? So when people are talking about nuclear fission and they talk about a critical mass, it's telling you what's the minimal amount of reactant I need to start with so that once I kickstart this, it continues on its own, okay? So once I kickstart it, I'm just going to continuously get energy from it, okay? And that would be, you need to start with that critical mass. And that will start then its chain reaction, okay? Now, there's one other type of nuclear reaction that at least we try to get energy from, and that's nuclear fusion, okay? Now, this is something that it happens on the sun, and that's where the energy from the sun comes from. But to do this in the lab is a lot more tricky than doing a fission reaction, okay? And so fusion is kind of the reverse. It's combining light nuclei to form a heavy one, okay? Whereas fission, we start with some large thing and we break it down, okay? That's relatively easy to do because you just need to hit it hard enough with something. Whereas if you want to combine, these small things into one, you have to have really perfect conditions. It's hard to get these nuclei to get close together, close enough to react. So that can be tricky. But if, when you get a fusion reaction to work or when a fusion reaction occurs, it releases a lot of energy, just like a fission reaction. And we would like to get a lot of energy from something, right? But like I said, it's hard to get these started. And so we actually have to put a significant amount of energy in to get it to work. And usually in order to get that to work, really to get the energy, you use a high temperature. And the temperature needed to start a fusion reaction would be called the ignition temperature, okay? And so it can be a very tricky process. That's why this isn't actually currently used to, get nuclear energy because it's so complicated. It's very difficult to do, okay? So this is something that hasn't been used to create electricity, okay? So again, when you have a nuclear power plant, they're doing fission reactions, not fusion. We'd love to do fusion because we can get a ton of energy. And the other nice thing is that we wouldn't have all the waste produced because it's combining things, and actually it's working with such light nuclei that what would be produced typically would not be radioactive substances, or they wouldn't be nearly as dangerous as what you're working with fission reactions, okay? And also, since it's very small nuclei that are used, we would almost have an unlimited supply of fuel, okay? Because those types of nuclei are very abundant, whereas the very large nuclei that we work use for fission, those are things that naturally are radioactive on their own. And so those are constantly being consumed even if we're not using them. Okay. So there's kind of a limited supply there. Okay. Now, the other stuff I do want to point out, I do have some other stuff put together on the slides that you can look through. It may be of interest to you. It all has to do with medical applications. Okay, so I know a lot of you guys are going into the medical field, and so it's important for you to know that this is something very applicable to your field. So even though we don't talk about the specific reactions, I've got some examples for you, but it's all the same basic processes. And so there's beta decays, there's alpha decays, there's electron captures that occur with particular radioactive isotopes that we utilize to our advantage in different medical techniques in order to track what's happening in the body, okay? And even to get certain things to work. And so I've got this slide, I've got a couple more slides that give you more information. So if you're going in the medical field, you might want to look at that. I'm not testing you over that, it won't be on the final. What you need to know is the basics of nuclear chemistry. So the basic particles, how to balance a reaction, and understanding a little bit about the stability and the different reaction types. Do you have an alpha decay, a beta decay, a fission, a fusion, things like that, okay? So don't forget, get your homework done for this chapter, get the quiz done, and then, you know, watch for exam 3. I will email you guys once it's opened up for review, okay? And you got your final next week, and reach out if you've got questions. Have a great weekend. Good luck on all of your finals, guys. I hope everything goes well for you, and have a great summer then.